Exercise 4.5 is a short exercise, but it's also useful because it shows you how to deal with perfect complements. So you are given the utility function of Mr. A, who drinks martinis, and that's the only thing that he likes in life, but he wants them in a particular mix, having 2 parts of gin mixed with 1 part of vermouth. And the utility function is given, so that's the one that we have over here. And in question A, you are asked to just graph a couple of indifference curves for different levels of utility. And now I've depicted some indifference curves here associated with utility level of 1, 2, and 3. And you need to show that regardless of the prices of the goods, he will never alter the way he mixes his martinis. And, well, if the price ratio is such that good Y is quite cheap compared to good X, such that you have to give up a lot of Y, a lot of vermouth in order to get more gin, so you have a very steep budget constraint, then the point of tangency is still a point on the red line, where the ratio between gin and vermouth in the consumption bundle is exactly 2 to 1. So, and if your price ratio would be different, such that the budget constraint would become something like this, we would still have a point of tangency on the red line. So, and also if it's very flat and your income is higher, then still your point of tangency would be here. So Mr. A, independent of the price ratio of gin and vermouth, he will consume in equilibrium the two in a ratio 2 to 1. Then in B, we have to compute the demand functions for G and V. So for gin and vermouth. And we know that we will mix in a portion 2 to 1. That's the first constraint. And the other constraint that we need to satisfy in equilibrium is the income constraint. So PG times G plus PV times V. Now, as in exercise 4.1, we can substitute the first equation into the second. But notice that here we didn't use the Lagrangian, we didn't differentiate things in order to get to our equilibrium conditions. But we simply observe that we have a case of perfect complements, so it has to be that in equilibrium this condition holds. But differentiation would not get you anywhere because we have a utility function that is not differentiable. So please note, if on the exam you're giving a utility function as like this one, don't start with the marginal rate of substitution or writing down a Lagrangian, because that will get you nowhere. Okay, inserting equation 1 into equation 2 to get rid of the units of gin. That will give us income is 2 times PG times the units of vermouth plus PV times V. So solving this one for V gives us that V is equal to our income divided by 2 times PG plus PV. And similarly, well, the number of units of gin is twice that number. So we have that the number of units of gin is 2 times I divided by 2PG plus PV. And this is the Marshallian demand. So it's demand as a function of income and prices. So this is our Marshallian demand. Okay, that's question B. Then we can continue with question C. And in question C, we need to use these results to arrive at the indirect utility function. Now, the indirect utility function is simply, we know that our utility, so going back to our utility function that we have over here, we know that this gives us a utility level U bar. So we know that our indirect utility function is identical to G over 2 or identical to V, because in equilibrium that amounts to the same thing. And we can plug in just one of the values that we derived in question B, and we arrive at the indirect utility function. I is 2 times Pg plus Pv. And we have expressed our utility as a function of prices and income. Finally, the expenditure function is the inverse of the indirect utility function. So fixing our utility level at the level U bar, and solving this expression for I, we get the expenditure function, and the expenditure function is equal to 2 times Pg plus Pv times U bar. And we're done with exercise 4.5.